What we're doing is looking back at second order linear, potentially non-homogeneous, but it'll start homogeneous, differential equations, which we can think of as modeling a spring mass system or an LRC circuit. But in general, they're just linear constant coefficient differential equations. Then we're going to use what we're starting to learn about with the Laplace transform to investigate behavior of these differential equations, or maybe more accurately, the solutions to the differential equations. So for example, let me get some annotation going. What we have is the following differential equation. In the t space, we have x double prime plus 9x is equal to 0. When we apply the Laplace transform, we end up in the S space. And what we get there is, let's see. So applying the Laplace transform, we get Laplace of x times s squared minus x of 0 times s minus x prime of 0 plus 9 Laplace of x is equal to 0. So that's just applying the Laplace transform to both sides of the t-space equation. And when I say t-space, even though it has x, it's x as a function of t. So you have functions of t. And in the S space, or that depend on t if you like, in the S space, the functions will depend on s. If we do a little bit of algebra, what we end up with is Laplace of x is equal to, let's see, s times x of 0. Let me actually put plus times x of 0 plus x prime of 0, and all that divided by s squared plus 9. So the Laplace transform of x is equal to all this here. Now in the t space, before applying the Laplace transform, we have that x is, well, we don't know. It happens to be graphed for us. So we have the solution curve on the right, the x versus t graph. So we can see what the solution curve looks like. And we do know techniques to find the solution curve. In the t space, we can apply the characteristic polynomial, find roots, and so on. And if you go through all this process, you'll find that x is going to be equal to c1 cosine of 3t plus c2 sine of 3t. So that's something that you can already do, or if you maybe forgot or didn't feel super comfortable, I'm sure with a little bit of review that you could do, no problem. But instead of just going through the process of finding the characteristic polynomial, finding the roots, and et cetera from there, coming up with the solution curve, what's interesting is just to look in the S space. And let me see if I can move. Oh, good. I just want to move this down so a little bit more white space between the two. Okay, sweet. So what we are going to do here is look instead at the Laplace transform that is in the S space and see if we can determine what type of behavior the solution curve will have just from that Laplace transform. And in particular, what we'll do is we'll look at poles. So it's maybe worth reminding ourselves, what is a pole? And to answer that, it's also worth reminding ourselves what is a root. So Lx of S is, actually I should say this, S is a root of L of X, which depends on S. if and only if the following is true. If and only if L of, actually I should change that. Instead of S, let's call it something else. A is a root of L of X of S, if and only if L of X of A is equal to 0. Okay. So that's the definition of a root. Essentially, you plug A in for S, and what you get out is 0. That's a root. We would say that A is a pole in a very similar way. A is a pole, P-O-L-E, of L of X of S, if and only if something similar is true. It's not L of X of A, it's, how to say, 1 over L of X of A is equal to 0. Another way to think about it is if you can substitute A into the denominator in a rational expression, and what you get out is 0 in the denominator, that would be another way of saying that A is a pole. For instance, just to kind of make sure that that makes some sense, that this is useful to you, if we look at the following function, L of X is equal to S times X naught plus X prime of 0, all divided by S squared plus 9. If we're looking for values of S, what S values can you plug in that will give you a pole, or that would be a pole? Said another way, what S values can you plug in so that the denominator is 0? So would you just say in private chat what you think those are? Or if you're not sure, say not sure. It just lets me know to maybe say more about it. So what are the poles of this thing that I've highlighted in red here? That is, what values of S would have the denominator be 0? And again, if you're not sure, it's okay. And I already see some potential for kind of needing to say a little more, which is S can be real numbers, or it could also be a complex number. So consider S to be complex in general. So what real or complex number could you plug in for S? And real numbers are complex numbers, but complex is just more broad. Which I'm going to write that down just because I think it's worth being clear about that. How do I want to write it? Let's write it like this. So just for future reference, when you're looking at complex, I'm going to put this on the right. The complex numbers, as a set, they do include the real numbers. So real numbers are complex numbers, but not all complex numbers are real numbers. Okay. I'm looking back over the answers. Okay. So once I made the comment about real complex, maybe it seemed a little more clear. In fact, the poles in this case, or the values that you could plug in for S in order to get the denominator of L of X to be equal to 0, that is this S squared plus 9, those are plus and minus 3i. And if we then look here at these values, exactly what we get are 3i up top. I want that to be red to correspond. And then in the bottom here, we have minus 3i. All right, so good. We've got those values there. And if we change the differential equation up top, that would change the Laplace transform, and it would then change the, excuse me, it would then change what we saw on the left. Now, someone asked, so the S-plane is a complex plane? Yes. Yep. Yeah, good question. The S-plane is a complex plane. So you can think of the vertical axis as being the imaginary axis and the horizontal as being the real. Yeah, good. So now the big idea here is to say, if we look at just the poles, can we determine what's going to happen on the right as far as the solution curve? What's it going to look like? And I'm just looking over real quick to see what I want to keep and what I don't want to keep. Kind of like having a lot of this, but let's, yeah, unfortunately, let's erase it pretty much all. Now I'm going to try something here. I'm going to try to occlude what's happening on the left or on the right. Oh, perfect. That just to double check, the right x versus t graph, that's blacked out, right? For you? Like you can't see it? Okay, sweet. So now imagine we do something like this. So here's why I'm doing this, because, and I'll bring it back shortly, but let's say that we do something like this. We change the damping now to be something positive. Actually, I'm going to change it to be like this. Okay. Now, if we ignore the poles for a second in the S-plane, we could just simply look at the differential equation that is x double prime plus 3x prime plus 9x is equal to 0. We could just look at that. And maybe it's worth kind of really reinforcing that that's in t space. We could look at that, and then we could apply the characteristic polynomial and go through that process. We could use other techniques to determine the damping type. But instead of doing that just from the t space, it's both interesting and can be useful to look at the poles and then decide what kind of damping it's going to be. Now, I've chosen to occlude this box over, or to obscure this graph so that we don't see what the solution looks like right away. Now, based on what we see here, I'm just kind of curious, and it's more of a yes or no answer. Are you able to look at this and quickly determine the damping type? Maybe yes, maybe no. Can you like right away say, I know what kind of damping it is? And if you do know, maybe just say, I think I can right away tell it's damping, blah, blah, blah. And if not, just say, yeah, I don't know by looking at it. I would assume most people, including me, wouldn't immediately know, but maybe I don't know, maybe you've developed that number sense. It could be possible. Okay. Now yeah, thank you for those who gave feedback. I appreciate it. Now you could, find the characteristic polynomial, look at the discriminant and so on, and that would tell you about the damping type. But instead of going through that process, what I'm kind of trying to motivate here is that we could then just look at the poles and hopefully have a guess of what's happening over on the right. So for instance, thus far, I'm going to erase this and I'm going to start drawing some graphs. First, let me draw a bunch of S-planes. Some of the axes might be a little crooked. Apologize in advance. There we go. And there we go. Okay. So what I'm replicating here is S-plane on the left and X versus T solution on the right. So far, what we've seen is that when we had the two poles here and here, what that gave us was, okay, I can do this, was a solution. Let's make this not look like garbage. Come on, here we go. All right, this is it. Yeah. So smooth. Maybe some of you are better with a mouse, but I have such a hard time with a mouse. Okay, that looks okay-ish. So this is what we got. Now, in this particular example, we would like to know when we have those two poles that are now off of the vertical axis, so they're off the imaginary axis. They have something non-zero real part and something non-zero imaginary part. We'd like to know what's happening, question mark, over here on the right. And if we do something like this, where now we have it be 6, what's going on there? Well, what's going on there is, and you see a circle and an X. The reason there's a circle and an X is because it just represents there being two X's at the same spot. So instead of having two X's like perfectly overlap each other and you can't tell that there are two, it adds the circle to say, look, there are two different things here. So when that happens, we'd also like to know, what's going on the right. So now let's see. Let's get rid of this box and we can kind of see what happens. Rid of the box, eraser, boom. Okay, cool. I like that. That was a kind of exciting reveal. Well, exciting for me. It makes me lame, but I like this stuff. So what you have is then a curve that drops off pretty quickly. It looks like maybe a critically damped or what's the other one? Over damped. So it kind of drops off and then just kind of approaches like this. If we go back to the case when the damping was 3, we've got something like this, which looks to me kind of like underdamped. Let's see. Kind of like this. Oops. No. All right. Kind of like so. There's one other, which I'll kind of leave for the moment, but the idea is we want to be able to say, looking at the poles, or one thing we'd like to be able to say is, looking at the poles, can we tell what kind of damping there is? Like, what's the damping type? Is it underdamped, overdamped, and so on? So I think it's kind of illustrated clearly so that we can see what the damping type is. But there are many other questions you might ask. And what I'm going to do now is list some questions you might ask and things to think about that you'd want to determine. They won't necessarily be exactly in the order in the lab instructions. I'm not going like, here's number 2, here's number 3, but we'll talk about all the inherent ideas. So things you would want to ask once you see what the poles look like. So by looking at the poles, P-O-L-E, by looking at the poles, can we determine the following? So one such thing would be, can we determine damping type? So there's one thing. Another thing might be how fast the solution goes to 0 as t goes to infinity. It had some nice indenting with the ABC and then it got rid of it. That's too bad. But how fast the solution goes to 0 as t tends towards infinity. Other things you might ask are, let's see, looking at the lab instructions, reminding myself, oh yeah, how do the initial values affect the poles / solution, question mark. So that would be another thing we might ask. And then I think a final thing that we might ask would be, can we determine resonance or beats? So these are different things you would ask about making predictions about the solution curve based on the poles. So being able to look at those poles and say, we can decide that the solution curve will, let's say, tend towards zero quicker if such and such is true about the poles. So being able to identify characteristics about the solution curve from the poles. Now, let's see. Some of these I'll just kind of leave for you to explore. Otherwise, I'm just taking the joy of discovery from you, and then it's kind of not as useful to you or as interesting. But one thing I do want to maybe talk about a little bit more is the following. With these damping types that we have on the left, all of them involve an undriven system, if you like thinking about the spring mass example. All of them have a stem from a differential equation that's homogeneous. If we change that to be a non-homogeneous, so we introduce, in a physical sense, a driving force, and we update it, now we notice something interesting happening here. I'm actually going to simplify it a little bit by going back. Okay. Now, just by looking at this, again, I would kind of expect that maybe it wouldn't be clear, but perhaps it is. Would you tell me whether you're able to say if there is resonance or beats? One of the two. There is one of the two. It is either resonance or it's beats. Are you able to say which of the two it is? And I would expect not, but it's possible. And usually we would look at the graph to be able to say, the graph of the solution curve. That it's not very clear, to me at least. You might be able to subtly tell, but it's not super clear which of the two. So when I ask if you could tell, if you would be able to tell, it would be by quickly kind of computing frequencies, or like being able to just see from the numbers, like the coefficients, and let's say this value from there. But I would guess not, but I'm just kind of curious. Would you tell me, can you tell if it's beats or resonance or not? If you can tell, maybe say what you think it is. And if not, it's fine. I would expect not. And I would not be able to immediately look and say, I'd have to kind of do some computations in my head. Okay. Thank you to those who put something in chat. I appreciate your feedback. So it seems like most of the guesses were beats, and it is in fact beats. You can kind of tell from the graph by, let's say, I should get the right color, kind of doing this. So notice if I do this straight line from peak to another peak, some of the peaks are below, which if it was resonance, the peaks would just grow. So it doesn't seem like it can be beats, or it doesn't seem like it could be resonance because the peaks aren't strictly growing. And moreover, it looks like it might be kind of beats because some of the amplitudes are larger than or between two amplitudes, other amplitudes are smaller, which is what you have with beats. The amplitudes shrink and then they grow then shrink. They don't just strictly grow like in resonance. So it is beats. Another, graphically, we can just subtly tell. Another way we could tell is by looking at the frequency of both the complementary and then the particular solution. So the frequency of the complementary solution, that frequency happens to be 3. And then the frequency of the particular solution, that happens to be 1. And one of the ways that I can see the particular solution frequency is it's just this value. And the frequency of the complementary solution, it's going to be, when it's undamped, it's just going to be the square root of this value. So that's where the 3 and the 1 come from. Whenever those are different frequencies, that's when you get beats. Different frequencies is beats. When they're the same frequency, that's when you get resonance. If we leave the left side alone and we just compute now the frequency, or we change the frequency rather, for the driving force and update it. And I also am going to increase the amplitude just to make it a little more noticeable, like there. Now we can see how the amplitudes grow. So now we have resonance. Now it's then worth asking, if we change the frequency back to being different, and maybe, again, I'm going to change the amplitude just so it's a little more extreme, and we convert between beats in this case to now resonance in this case, you may be able to see or take a guess. Sorry, just stifling a yawn there, and yawns can be contagious, so I didn't want to infect you. Oh, I just thought of that. That's kind of interesting. It's a way you can infect people over Zoom with, with yawn. So if we switch between the two, you may be able to kind of notice the difference between resonance and beats, not just on the left, or not just on the right, but also on the left, that you can tell in the poles and in the solution curve graph. So that's kind of addressing part D here. Maybe I'll just say one other thing, and that is, how do the initial values affect the poles? So you'll notice that if I, let's say, change the initial values, and let's simplify it for a second. Let's go back to the first one we had. So now there's no driving force. In the first case, when we had x of 0 is equal to 4, that means the starting position is 4, and x prime of 0 is equal to 0 means the initial velocity is 0. So it starts at 4, and it's like not changing its position at that moment. But then, because of the structure of the differential equation, the physical system, if you will, then it's going to get pulled down. But for just one moment, it's not moving. If we change that to, let's say, 0, and actually let's keep 4. Let's keep the same position, but let's give it some upward positive velocity. I shouldn't say upward, but positive velocity. Let's set that equal to 4. We can see that it changes it. So initially it starts moving in the positive direction, but then kind of settles back into this oscillating behavior. But yet, if we look what happens with the poles, when we, I'm just alternating between these initial conditions, the right side changes, but maybe the left doesn't. And you might ask yourself, is it possible to change the initial values in such a way that the poles are changed? And you can actually see whether it's possible or not by looking at the Laplace transform itself in general and saying, how do we come up with the poles, and how does changing the initial values change the Laplace transform, / how can we get that to change the poles or not change the poles? So it's definitely worth looking at the Laplace transform in general. And when I say that, you can always take the Laplace transform of a general second order differential equation. That's certainly possible. And then you can answer the kind of question I was just asking about initial values. Okay, with that, I think that's all I have for things I definitely wanted to show you or say to you to kind of help you get started. So with that, you're welcome to head out if you like, or you're welcome to stick around and ask some questions if you have any. So if you're heading out, you have a good day. If you're sticking around, I welcome your questions. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.